Hello and welcome to episode 22 of ToKCast. And today it's an audio-only podcast. There's no video for this one. It's basically about another esoteric area of philosophy, one of my more favourite papers that David Deutsch has published over the years, The Logic of Experimental Tests, particularly of Everettian Quantum Theory. That was a 2016 paper that David published. David is very much the intellectual heir of Popper, so in this episode, not only am I going to be discussing that paper with a few little embellishments of my own, but also going back to have a look at what Popper said about many of the same issues. Obviously, Popper wasn't talking about Everettian quantum theory. He didn't understand that. He wasn't aware of it. He did struggle to try and understand quantum theory himself and failed to do so. Nonetheless, the material here about the kinds of experiments that exist in science and how science makes progress really find their seed in Popper's work, very early on as well, right back to his first book, back in 1934, I think it was, The Logic of Scientific Discovery. So we'll come back to that at some point. So this episode is somewhat a standalone episode, but it's also going to serve as an introduction to Chapter 11, the Multiverse, which is the next video and the next podcast that I'll be doing. That's going to spread over at least 3 more episodes. It's going to be quite a big one. I want to be able to explain lots of the experiments that force us to realize that classical physics just won't cut it in order to explain what's really going on. Now, the multiverse, which does explain what's happening in these experiments that I'll be discussing, turns out to be a testable physics theory. It's not an unfalsifiable interpretation, as it's often claimed to be. Even some physicists who purport to support the multiverse as the way of understanding what happens in quantum mechanical experiments say the multiverse is unfalsifiable, which seems to me to be a contradiction in terms. After all, if the results of those experiments were otherwise, there'd be no reason to invoke the multiverse in the first place. I've heard all sorts of prominent physicists go so far as to say that the whole principle of falsification ism, as explained by Popper, is obsolete because the quantum multiverse exists, or perhaps other multiverses exist. And because those other multiverses exist, but aren't testable, then we can jettison the falsifiability criterion. Sometimes people who follow Popper in this regard about the falsifiability criterion are sidelined as Popperazzi. As a fan of Popper, I'm yet to come across these people myself. You can tell people who haven't really read Popper, they are prone to say things like, Popper didn't understand you cannot categorically refute a theory in science, or he didn't realise that falsification isn't so straightforward. The problem with this is that Popper wrote many, many books on this topic. He didn't merely blog or tweet, he wrote hundreds of thousands of words basically about critical rationalism, epistemology, as applied to everything. He considered very many angles that people could object to falsification from. He encountered critics in his long life and he responded to them. Few stones were left unturned. Why he elicits such casual dismissal among some remains a mystery. Whatever the case, falsification, or another way of putting this, the experiment, is a crucial aspect of science. I should be a little bit clearer. The crucial experiment is a crucial aspect of science. And we'll be talking today about 2 different kinds of experiment that do exist in science. There's the crucial kind, the crucial test, being, as David describes it, the centerpiece of scientific experimentation. Crucial experiments can be conducted that would, if the results were just so, falsify quantum theory, or at least make it problematic. People who try to reject falsificationism in science tend never to grapple with this idea of the crucial experiment that could merely make a theory problematic. David has explained 2 ways the multiverse can be tested. Firstly, against so-called collapse interpretations. And secondly, against rival theories that purport that not everything that can happen does happen. So I'll make some remarks about that first thing, against so-called collapse interpretations today, but we'll basically be concentrating on the latter, that a crucial experiment would be able to decide between the everything that can happen does happen idea and the idea from classical physics that basically only one thing ever does happen. And an everything that could possibly happen actually does happen in physical reality is another term for Everettian quantum theory, or the multiverse. Falsification in many ways is just a very simple idea, but for many philosophers and scientists it seems too difficult an idea, and so they want to jettison it. On social media, we often find people rediscovering the Quine thesis, and we'll be talking about that today too. Now, the paper that David wrote in 2016, The Logic of Experimental Tests, I think that if you're really interested in the philosophy of science or epistemology more broadly, then you really should read this. It should be required reading for you. Yet it is hard going in places, and if you don't have a physics background, you might stumble over some of the nomenclature and some of the other formalism that's in the paper. But you can read it more or less by ignoring those few pieces of mathematical jargon and quantum physics stuff that's in it. What I want to do here is try and denude the paper of some of its jargon and attempt, however poorly, to try and reconstruct some of the arguments. I'm going to quote somewhat from the paper today, not hugely lengthy quoting, so that you can get a flavour of how clearly David writes about these issues. I really do think, however, there's no substitute for reading the original paper. It's absolutely seminal work, and do consult the original paper as linked to on my website. I'll have a link to that also here in the podcast. Some of the material in the paper can, of course, be found elsewhere, particularly in David's previous works, The Fabric of Reality back in 1997 and The Beginning of Infinity in 2011. However, there's much that's new in this paper, and it supplements and is supplemented by those books, and some excellent clarifications of key points in the philosophy of science, and as one may guess from the title, the actual role of the experiment in the sciences. Although the central concern of the paper is a defence of the role of explanation in science, and so an explanation both of explanation itself and the purpose of experimental tests in science, another crucial point emphasised throughout the paper, despite David's books and comments on the topic, is how quantum theory is fully deterministic. Despite what passes for high school and undergraduate teachings on the subject and what one finds in popular books and documentaries and even texts, quantum theory is not a theory about how the world is governed by laws that are probabilistic, or laws that bring true objective randomness into the world. In fact, there are no truly random processes. There may be subjective randomness. We may not have information within our universe to know what's going to happen next. That's subjective randomness. But it's all explained by purely deterministic laws. Everything is determined by the quantum mechanical laws of motion, and the general theory of relativity. And those laws of motion specify that what is observed to occur happens because of everything else that happens in physical reality. That is to say, the laws of quantum theory predict that prior to an observation, everything physically possible actually occurs, and all those occurrences come to bear upon the outcome that you do observe. Indeed, not merely prior to the observation, but during and after the observation, whatever is physically possible and can happen at those times does happen. Necessarily, an observer finds themselves only in one universe, and therefore observing only one thing, not many things simultaneously. Now, to my mind, this should be no more mysterious than that observers necessarily only ever experience a particular instant in time as well. They never experience many times simultaneously. Although they know that the past must have happened, and that the future will come, and that the past and future is just as real as the present, the observer can only possibly, at any given moment, experience the present. Now, another way of looking at this, and I'm taking this from an interview that David gave, and I'll link to that interview in the notes of this podcast, is about trying to just see an object in space. So if we imagine a statue about which a person can walk and view from any angle, at any instant the person might be found north of the statue, or south of it, or west, or southwest, or any position in a 360-degree space around the statue. What they cannot do is experience more than one's perspective on the statue simultaneously. Well, not without technology anyway. They can't view it from the north and the south, say. This is hardly a deep philosophical problem. We must stand somewhere with respect to the statue if we wish to view it. Even from above, we cannot see it all. Unless, and until we move, some places on the statue are hidden from us. Yet we know those places that remain hidden are just as real as the places we are observing at some given instance. Without those parts, the statue would perhaps topple or collapse upon itself, depending upon how large and massive a structure it was. What you are able to see depends entirely on what you cannot see. If it's a real and complete statue and not a hollowed cast, say, and we are not otherwise deceived. And this is easy to check if we just continue to change our perspective. So it is with quantum theory. What happens in the Two-Slit Experiment, for example, with single particles, is that all the possible paths are taken through the apparatus each time a particle is fired at it. But we necessarily only ever see one. And we know the other possible paths really do exist, because if you repeat the experiment often enough, you will eventually approximate all those other paths, like slowly walking around the statue to gain a different perspective. David uses the statue analogy to resolve some of the mystery about the nature of time. The subjective consciousness of an observer must experience only the present moment, and not the present, past and future simultaneously, for much the same reason that the statue viewer sees only one angle of the statue at a time. But I'm using that analogy here in an attempt to convey that if you take seriously what the Schrödinger wave equation predicts about reality, then all physically possible events actually occur even if you only ever experience one tiny slice of that reality at any given moment. The statue analogy actually shows how deep this idea of the observer having a particular perspective on reality runs, and it must have something to do with how quantum theory, which explains how an observer finds themselves only in ever one universe, is going to be united with the general theory of relativity, which explains how time is related to space and that times are just special cases of universes. The single perspective on the greater whole that any observer necessarily has is at once a very simple, common sense and true way in which we understand the space and events around us, but it should also be the way in which we understand better the nature of time and the nature of so-called parallel universes. Not actually parallel, because they can interfere. Now let me turn to a little bit of quoting from the original paper that David wrote, and I'll make some further remarks along the way. So David wrote, "In this paper, I shall be concerned with the part of the scientific methodology that deals with experimental testing. But note that experimental testing is not the primary method of finding fault with theories. The overwhelming majority of theories, or modifications to theories, that are consistent with existing evidence are never tested by experiment. They are rejected as bad explanations. Experimental tests themselves are primarily about explanation too. They are precisely attempts to locate flaws in a theory by creating new explicanda of which the theory may turn out to be a bad explanation." End quote. Okay, so my remarks on that. This is a key theme in the beginning of Infinity. The idea that science is all about experiments is a misconception, probably handed to culture by the education system. Indeed, it is the case that experiments are necessary in science, but they are far from sufficient, and although crucial, not central to the whole project. The purpose of science is explanation, not experiments. David's about to come to two different types of experiments that are performed and the purpose of those experiments, but it is vital here to notice the point. Bad theories, or silly ideas, that purport to be about the physical world do not need to be tested to be shown worthless. They can be dismissed outright as bad explanations without ever being tested. This point was made in the Fabric of Reality with the so-called grass cure thought experiment. If a herbalist comes to you and says that eating 1 kilogram of grass is a cure for the common cold, what's the reasonable response? Well, of course it's to reject the suggestion, but on what basis? Surely not that it's untestable, because it is. You could eat a kilogram of grass if you want to, but who would ever bother doing that? What is truly missing from the grass cure theory is any explanation. How on earth is the theory supposed to work? Unless the herbalist can give an answer that is a good explanation that explains how the 1 kilogram of grass actually interacts with, let's say, viruses and destroys them or otherwise is able to alleviate symptoms, then we know we have an explanationless theory. And if they do, and this is key, such an explanation must be able to account for why it's exactly 1 kilogram and not 0.9 kilograms or 1.1 kilograms or any other of an infinite number of other explanations. Of course, I'm just noting here that many herbalists and the like do suggest something akin to grass cures, and they do attempt explanations, but they're never good explanations. They're often nonsense. They conflict with some other actual piece of science. So if you just think about homeopathy, for example, the idea that water remembers things that was once diluted in it, so it remembers certain kinds of medicine once diluted in it, although apparently it forgets the sewage that was also once in it. This conflicts with the idea that chemicals are the agents that can actually do pharmacological work, and not vibration or other such nonsense like that. Okay, let me go back to David's paper, and David writes, quote, "Scientific methodology in turn does not, nor could it validly, provide criteria for accepting a theory. Conjecture and the correction of apparent errors and deficiencies are the only processes at work. And just as the objective of science isn't to find evidence that justifies theories as true or probable, So the objective of the methodology of science isn't to find rules which, if followed, are guaranteed or likely to identify true theories as true. There can be no such rules. A methodology is itself merely a philosophical theory, a convention, as Popper in 1959 put it, actual or proposed, that has been conjectured to solve philosophical problems and is subject to criticism for how well or badly it seems to do that. There cannot be an argument that certifies it as true or probable any more than there can be for scientific theories. End quote. So there, David is pointing out that in the same way that we can't prove as true scientific theories, we can't prove as true philosophical theories either. We can't show as true this entire idea about demarcating science from non-science using the falsification criterion. It's the wrong question. How do you know that the falsification criterion is actually true? Well, that undermines the whole idea of critical rationalism, where it's all about finding errors. You'd need to find out what's wrong with the falsification criterion. Just more broadly on that point, this is one of the most contentious pieces of philosophy that Karl Popper and David Deutsch, or indeed any Popperian or critical rationalist, proposes about how science works. It's poorly understood, and the opposing worldview is still very much the dominant philosophy of science, even though it's completely false. The false idea, subscribed almost universally by scientists, philosophers, and laymen alike, is that science somehow provides a way of demonstrating that certain theories are true, or close to true, or probably true. And moreover, that the more one gathers evidence for some theory, call that theory T, then the more likely T is to be true. What David, following Popper, is saying here is that there is no such process as that. There is no method in science, no set of rules to follow that can demonstrate theories as either true or probably true. And no method in philosophy, for that matter, to demonstrate that philosophical theories are true or probably true. The whole purpose of science is not to support theories with evidence. This is a complete misconception. The truth is that science is about correcting errors in our explanations. This is a completely different view of science to what most people have. Now, some admittedly have read a little bit of Popper, or maybe some of David Deutsch, but are afraid, or perhaps confused about, fully taking the step to actually appreciate the significance of this. Now, the reason I say afraid there is because it seems to me that some have the concern if they too strongly endorse even a correct theory like this, one might seem dogmatic. So often people profess to partly support Popper, that falsification is kind of a good idea, but sometimes we still need confirmations. You can't mix Popperian critical rationalism and falsifiability with any kind of confirmation or Bayesianism. They don't mesh together. And reading Popper really illustrates this quite well, because Popper's entire philosophy is about rejecting the idea that we can have true or probably true theories. So there's no way in which we can simultaneously endorse Popper's idea of rejecting true and probably true theories while simultaneously accepting the possibility of true or probably true theories. This would be a perversion of logic. This would simply upset the law of the excluded middle. Things cannot both be true and not true simultaneously. I'm just observing that there are many smart people, many prominently smart people, who struggle to grapple with the centrality of what science is even all about. Now, many scientists today do not want to call themselves Popperians or critical rationalists, which means they do not want to endorse the idea that science is not about supporting theories with evidence. And so they call themselves empiricists, or sometimes Bayesians these days. Now, I've got a detailed critique of Bayesianism as a philosophy of science or as an epistemology, and you can just Google my name, Brett Hall, Bayesian epistemology, and it will bring up an article about that. Just in brief, however, a Bayesian is essentially someone who thinks that repeatedly observing a phenomena allows them to build up a probability that a particular theory is true. So they can assign a number between 0% and 100% that a given theory is true, or something like that. So if the result of an experiment continues to come out the same way, the probability number, climbs closer and closer to 100%. But perhaps it can never quite reach 100%. Maybe these people are fallibilists. They don't think you can be 100% certain, but you can asymptotically approach that 100% number. If you're just interested in probably true theories, perhaps 90% is okay, or 95%. Or perhaps 99.999995% at the 5 sigma confidence level, if you understand what that means. People in physics especially, astrophysics in particular, make a big deal about the 5 sigma confidence level. But one need only consider the question: what probability would a Bayesian have assigned to Newton's theory of gravity being true at any time prior to its having been found false? Now, if a scientist were actually a Bayesian in the year 1900, say, then it would seem that every experiment ever devised to test Newton's theory of gravity always corroborated it. Newton's theory correctly predicted the outcome of every well-designed and executed test prior to it and up to and including the year 1900, and maybe a little bit later. A Bayesian could do statistics on any prediction you like and generate some number, and the number would be pushing the ceiling of the magic 100%. Newton's theory of gravity, according to that philosophy of science, would be very, very, very close to being certainly true. And yet ultimately it was shown to be false. It was shown false by a crucial experiment on May the 29th, 1919 by the great physicist Arthur Eddington, who measured the amount of light by which starlight was bent as it passed by the sun during a solar eclipse. Newton's theory predicted one number, Einstein's another. The amount of bending was in agreement with Einstein's theory of general relativity, but not in agreement with Newton. Newton's theory was then refuted. So far from being very, very close to true, because of all the experiments that it had ever predicted the outcomes of up until then accurately, it was shown false by a crucial test that pitted it against a rival. Now general relativity is in the same position that Newton's was prior to around 1900. But it's not probably true or anything like that. It contains some truth, and more truth than Newton's, which was closer to true than any random guess would be, but in neither case can we say that the theory is true, only that it contains some truth. We don't know what truth that is, and it doesn't matter anyway. The theories can be used to help us control reality around us by making predictions and helping us to create technology to solve our problems. At any time, however, to paraphrase Thomas Huxley, the beautiful theory could be slain by some ugly fact. Indeed, we have to expect that it will be at some point. General relativity is at odds with quantum theory. They are mutually incompatible for reasons that I won't go into now beyond the scope of my present piece. But in brief, the dispute might come down to a disagreement about whether the most fundamental parts of reality consist of discrete or continuous quantities. David has said in other places, and I agree, it would be far better if we had all decided to call scientific theories scientific misconceptions to remind ourselves of how tentative they are and that they will one day be superseded by some better misconception. Back to quoting David's paper. Quote, "Expectations apply only to some physical events, not to the truth or falsity of propositions in general, and particularly not to scientific theories. If we have any expectations about those, it should be that even our best and most fundamental theories are false. For example, since quantum theory and general relativity are inconsistent with each other, we know that at least one of them is false, presumably both. And since they are required to be testable explanations, one or both must be inadequate for some phenomena. Yet since there is currently no single rival theory with a good explanation for all the explicanda of either of them, we rightly expect their predictions to be borne out in any currently proposed experiment." End quote. Just my exposition on that. In other words, although we know at least one, but presumably both, of our best, deepest theories of physics are false, there's no rival theory out there to replace them that can do the job of both just as well. And we must just recall that when we refute a theory, we did not discard every single part of the theory. As a rule, very much is preserved. A short example from astronomy will suffice. Ptolemy explained that the universe was geocentric, an arrangement where the Earth was at the centre, orbited by smaller spheres in circles. Copernicus theoretically did away with parts of this. He replaced the Earth with the Sun, but he kept the circular orbits. Kepler likewise came and replaced the circles with ellipses, and then Galileo used observation to show how the sun-centred model was superior, and that there were objects orbiting Jupiter. Newton then provided a universal physical law in mathematical form, allowing orbits to be precisely predicted. And finally, Einstein showed how Newton's law was a good approximation to a better theory of the behaviour of space-time, which explained why the paths around the sun were how they were. So each new improvement preserved much of the past, and crucially the idea, for example, that the orbits were actually occurring, even if what was orbiting what and why changed as things improved. So refutation of a previously good theory, whether experimental or not, does not do away wholesale with everything that was valuable in the theory. It preserves much, although ultimately demonstrating how the theory is fatally flawed and therefore ultimately false, with the proviso, as David mentions in a section I'm about to quote, that theories are never entirely logically contradicted by some experimental observation, but this is a technical point we can return to later. We also might observe here that people often object to the quantum multiverse idea on the basis that, well, the next theory that replaces quantum theory and relativity might do away with the parallel universes. I would find this as unlikely as the next theory of gravity doing away with orbits, or the next theory of genetics doing away with DNA. More likely, that part of the theoretical apparatus will be retained. So DNA will be retained as in whatever the successor to genetics is going to be. Orbits will be retained in whatever the successor to the best gravitational theory will be. And whatever the successor to quantum theory will be, will retain the idea of many universes. Back to the paper, short quote from David. He writes, quote, "A test of a theory is an experiment whose result could make the theory problematic. A crucial test, the centerpiece of scientific experimentation, can, on this view, take place only when there are at least two good explanations of the same explicandum. Good, that is, apart from the fact of each other's existence. Ideally, it is an experiment such that every possible result will make all but one of those theories problematic, in which case the others will have been tentatively refuted." End quote. Now this is an amazingly important and clear articulation of what experiments are. Experiments test theories, but what can the results do? Well, interestingly, if the result of an experiment conflicts with a theory, it does not necessarily rule out a theory. So take, for example, the more or less frequent media hype that can surround certain high-energy physics observations that are reported quite often as Einstein proved false. Perhaps one of the more famous examples was about an experiment at the Large Hadron Collider, you can Google this one, where neutrinos, these little particles, apparently exceeded the speed of light, and that violated special relativity. However, it turned out there was a cable incorrectly connected or some such. Now, the results were actually false. The results of the experiment were false. But even if the results were true, even if the neutrinos were exceeding the speed of light, this would not prove Einstein false, or possibly cause us to reject relativity theory. What it would do is make relativity theory problematic. Relativity theory would still be the best theory about how fast things can move and what happens to things as they move relative to one another. So a test of a theory, an experiment, even if it disagrees with the best theory going, is not a reason to reject that theory. After all, if you reject that theory, then what theory should you use? The second best theory? There's almost never a second best theory. But even if there were, that second best theory is second best for a good set of reasons. And if those reasons include things like it cannot explain phenomena A, B, C, D, E, and F, while the first best theory can, then there still won't be a reason to turn to that theory in place of the first best. There is only one way. An experimental test of a theory can result in us rejecting our best explanation. And that is when we actually have an equally best rival theory that explains everything our other best theory does, plus it explains the outcome of the new experimental test. This kind of experiment is called a crucial test. It is that rare type of test, like Eddington's observation of the bending of light, that allows us to decide between two theories that make incompatible predictions about the outcome of the test, but that otherwise are, until that moment, equally able to account for all other phenomena. As it is now, of course, general relativity is able to account for far, far more than the mere bending of starlight during eclipses over what Newton's theory can. Newton's universal gravity, as brilliant as it could get people to the moon, is left in the distant dust by Einstein's general relativity, who could not only get us to the moon if we wanted to, but it also gave us GPS. It explained neutron stars, predicted the existence of black holes, which were observed, and much more besides, none of which Newton's theory comes close to accomplishing. David writes in the next section, quote, "The existence of a problem with a theory has little import besides, as I said, informing research programs, unless both the new and the old explicanda are well explained by a rival theory. In that case, the problem becomes grounds for considering the problematic theory tentatively refuted." End quote. So what David's done there is de-emphasising the supposed centrality of the experiment to the whole project of science. Science is a knowledge creation, in the form of bold explanations, machine. The genuinely difficult part is positing grand explanations for what's actually going on in the world. Of course, those explanations need to be testable, but if the explanations account for the phenomena and survive the tests, the explanation then becomes a central concern of all of civilization, who can then go about using it, making practical use of that science. For example, to create technology, treat disease, solve other problems, and so forth. An experiment that disagrees with some great theory just makes the theory problematic. But if we did find some experiment that, for example, could not be explained by quantum theory, say, or seemed to refute quantum theory, that'd be a problem for quantum theory, but not a grounds for rejecting it. The now problematic quantum theory would still be used to create technology, solve problems. Essentially, everyone would carry on more or less as before with respect to the theory and regard it as a genuine description of reality to some extent. But there would be an unsolved problem. And once more, as David observed previously and what we're about to get to as well, the problem might just be with the apparatus. And if it's not a problem with the apparatus, it could be a problem with us not understanding some subtlety of the theory. Or it could be that the theory is genuinely not the best theory because someone, somewhere, has just created something better, but is yet to publish it. And when they do, it will do all that quantum theory ever did, and explain the problematic result that quantum theory couldn't. And in that case, the test that created the problem in the first place now becomes a crucial test. As David writes, quote, "In contrast, the traditional inductivist account of what happens when experiments raise a problem is, in summary, that from an apparent unexplained regularity, we are supposed to induce that the regularity is universal, or according to Bayesian inductivism, to increase our credence for those theories predicting that. While from an apparent irregularity, we are supposed not to drop the theory that had predicted the regularity, or to reduce our credence for it. Such procedures would neither necessitate nor yield any explanation." End quote. That's absolutely crucial. Under the prevailing view of how science works, if an experiment critically wounds a theory such that it is once and for all falsified and so liable to be rejected, then where do we jump to? If we reject our best theory based upon an experimental refutation, supposedly, and there's no rival, the process of rejection does not provide any new explanation for us. The negation of a theory is not a new theory, David has explained. And David writes, quote, "In any experiment designed to test a scientific theory, T, the prediction of the result expected under T also depends upon other theories, background knowledge, including explanations of what the preparation of the experiment achieves, how the apparatus works, and sources of error. Nothing about the unmet expectation dictates whether T, or any of those background knowledge assumptions, was at fault. Therefore, there is no such thing as an experimental result logically contradicting T, nor logically entailing a different credence for T. As David writes in a footnote in this paper, that is known as the Duhem-Quine thesis, Quine 1960. It is true and must be distinguished from the Duhem-Quine problem, which is the misconception that scientific progress is therefore impossible or problematic." End quote. Now, when I first read that back in 2016, I was so excited because it was something new I learned about how to respond neatly to the Duhem-Quine thesis objections that are often raised if anyone gets into discussions about Popper and falsification. It's usually the first thing that comes up. It's usually the first objection that people have, that upon learning the headline that Popper created the demarcation criterion of falsification, and that if you falsify a theory, if you're able to falsify a theory with an experimental test, then you've got a way of distinguishing scientific type knowledge from other kinds of knowledge, like philosophical knowledge. You can do experiments in science in order to show things are wrong. But sometimes in philosophy, rather often, you can't. Sometimes in maths you can't. Sometimes in morality you can't. And in fact, in some of those places, it's undesirable to even try. Should we really try again to see if communism works? I don't think so. I think there's other reasons to reject it. We don't need to experimentally test if next time all those people won't be massacred or all those people won't starve. Instead, we can refute it based on argument. But here, with respect to the Duhem-Quine thesis, the thesis itself is correct. But what many people assume follows from it is not. The Duhem-Quine thesis is, in my words, when an experiment is conducted and the result disagrees with some theory T, then it's not logically the case that T must be false. Logically, it can always be the case that the experiment was conducted badly. The method wasn't followed or the method was faulty in the first place. The apparatus was faulty or operated incorrectly or some other background assumptions were false. So, some object, using this thesis, that there's no such thing as a crucial test because it might not be the theory T that's false, but rather it could be the experimenter or the equipment that is incompetent. Sure, So far, so good. But David's point here is that Popper's philosophy of science is the correct epistemology of how science generates knowledge, and although it can always logically be the case that an experimental error might be at root a reason for an apparently problematic observation, this does not have any lasting effect on how science makes progress. Scientific progress actually happens in spite of this. As with the faster-than-light neutrinos, it might have been the case that the observation was a problem for relativity, or it might have been background assumptions in the form of badly connected cables. That turned out to be the case, as Klein warned it always could be. And that had no bearing on the methodology of science. Indeed, it is the methodology of good science that uncovers such problems in the first place and allows things to keep moving in the right direction. So just to emphasize that again, the fact that a single experimental test apparently disagrees with your theory, so you've apparently observed something moving faster than the speed of light, and this is a problem for special relativity and general relativity. It's a problem for Einstein's relativity. So what? So what? Continue to repeat the experiment in many, many different ways, and you might just find out that your cables weren't connected correctly. And so you've used the critical method. You've still used Popperian epistemology. You've been critical of the criticism. You've criticized the criticism. The criticism was, there's neutrinos, there's particles traveling faster than the speed of light, and this appears to be a problem for special relativity. Well, now let's criticize that observation. Let's see if that observation stands up to being repeated by many different teams around the world, or replicated by any other group of physicists. And if it's not, then the problem is not with relativity, the problem's with your experiment. And that has been found by the method of falsification. We've falsified the bad observation. Back to quoting David, quote, "But as I have said, an apparent failure of T's prediction is merely a problem, so seeking an alternative to T is merely one possible approach to solving it. And although there are always countless logically consistent options for which theory to reject, the number of good explanations known for an explicandum is always small. Things are going very well when there are as many as two, with perhaps the opportunity for a crucial test. More typically, it's 1 or 0. For instance, when neutrinos recently appeared to violate a prediction of general relativity by exceeding the speed of light, no good explanation involving new laws of physics was, in the event, created. And the only good explanation turned out to be that a particular optical cable had been poorly attached. See Adam et al., 2012. End quote. So what I'd like to say about that is that forming theories to explain things adequately is very hard. It is a highly creative process that takes understanding what seems to be happening in the world and how to communicate the idea clearly in a language others will understand. Sometimes, though this is not necessary, it can require appreciating some of the current theories and what problems there are with them. In short, it requires background knowledge and then lots of imagination. So because of some of these factors, there is a poverty of good explanations in the world, but a proliferation of false and bad ones. Now here I just want to turn to a section of the paper that I won't quote, but instead will put into my own words about the special case of quantum theory. And this is really important, and this is probably, I guess, the center of the bullseye as to why I'm doing this podcast now, because as I say, in the next 3 episodes of ToKCast, especially the video version, we're going to be talking about this. And so, if you've got 2 explanations, say, we've got explanation capital E, and that's an explanation for everything happens, the everything happens explanation. Everything possible happens. Technically speaking, everything physically possible happens. So let's call that E. It's a theory about what can possibly happen. So the everything physically possible happens theory means that A happens and B happens and C happens and so on. All these things actually happen, okay? Now, we're going to put that up against another theory. Call that explanation D. And explanation D only predicts that one thing happens, X. So if that one thing that D predicts happens over and over and over again when you perform an experiment, well, the interesting thing is that E, the everything possible happens theory, is not refuted by experiment because it also predicts that that thing should happen, as well as everything else. But what it cannot explain, okay, what E cannot explain, is why only that thing should happen, while D does explain why that one thing happens, and only that one thing happens. So although experiment can't refute E in that way, the fact it's a bad explanation does. Of course, if something else happens, like B rather than X, then D is roundly refuted, but E is not. The strange thing here is that even if X is observed every single time, which makes B apparently more accurate, E might still be actually true or closer to true. E might still be the best theory or closer to being the true theory. It could just be a coincidence that X happens all the time, but that's a poor explanation. And this is why poor explanations might still be more true than good explanations, as David says at the very beginning of his paper. E could be augmented with G, where G explains why X is found to occur every single time. Okay, I'll quote a little bit of David here, and he writes, quote, "Thus, it is possible for an explanatory theory to be refuted by experimental results that are consistent with its predictions. In particular, the everything possible happens interpretation of quantum theory, to which it has been claimed that Everettian Quantum Theory is equivalent, could be refuted in this way, provided, as always, that a suitable rival theory existed, and hence it is testable after all. Therefore, the argument that Everettian Quantum Theory is itself untestable fails at its first step. And I shall show in section 8 that it is in fact much more testable than any mere everything possible happens theory." End quote. Okay, and just my remarks on that. As David's about to explain in a quote I'm about to provide, but let me emphasise, the multiverse theory is testable because it predicts that, for example, all possible paths are taken by particles through a double-slit apparatus experiment. And that is exactly what we observe when we repeat the experiment again and again with lots of particles. If the particles were instead just over and again striking the screen in one place, point X, point X, point X, point X, the electrons or the photons are going through the double-slit apparatus and just hitting the same point again and again and again, we could refute the everything possible happens multiverse theory because strings like that are not expected. As David says, quote, "This is because a string of repeated observations, like X, is not expected to happen, even though it asserts that everything, including that string, actually does happen. This is no contradiction. Being expected is a methodological attribute of a possible result, depending, for instance, on whether a good explanation for it exists, while happening is a factual one. What is at issue in this paper is not whether the properties expected to happen and will happen are consistent, but whether they can both follow from the same deterministic explanatory theory, in this case E, under a reasonable scientific methodology. And I have just shown that they can." End quote. So that, everyone, would seem settles that. The multiverse theory is testable. Now, I've got a few more little quotes here that I'll provide. I just might make a remark on the further testability of multiverse theory. Now, as far as I know, the first time it was published was in 1984 in a paper that David wrote. And in that paper, he discussed an experiment that could be performed, an interference experiment, using artificial intelligence technology. This was also later published in a popular science book by Paul Davies, and I think it's Julian Brown, and they wrote a book called The Ghost in the Machine, where they interviewed a wide variety of physicists about their understandings of quantum theory. And this is one of the first times I encountered David Deutsch, in fact. Now, in that book, David also gives a lovely popular account of the experiment that could be performed that would refute all collapse theories, all other theories about quantum theory, all other interpretations of quantum theory, and not refute the multiverse version of quantum theory. Okay, but back to this paper for now. Quote from David. Quote, "Explanation itself cannot be defined unambiguously because, for instance, new modes of explanation can always be invented. For example, Darwin's new mode of explanation did not involve predicting future species from past ones. Disagreeing about what is problematic or what counts as an explanation will in general cause scientists to embark on different research projects, of which one or both may, if they seek it, there are no guarantees, provide evidence by both their standards that one or both of their theories are problematic. There is no methodology that can validly guarantee, or promise with some probability, that following it will lead to truer theories, as demonstrated by countless examples of which Klein's is one. But if one adopts this methodology for trying to eliminate flaws and deficiencies, then despite the opportunities for good faith disagreements that the criteria still allow, one may exceed in doing so." End quote. And I think that's really important. I have read some criticism of David's criterion for what constitutes a good explanation, That being that hard to vary is not well defined. But there we find a good response. New types of explanations can always be created, not only simply new explanations, okay, new types of explanation, new modes of explanation. And so a definition that is unambiguous could rule out legitimate explanations to come in the future. And so that's why hard to vary can't be constrained too much. We're certainly after hard to vary explanations, but if we make hard to vary too hard to vary, then we won't allow for new modes of explanation in the future. Going back to quoting the paper from David, quote, "We have become accustomed to the idea of physical quantities taking random values, with each possible value having a probability. But the use of that idea in fundamental explanations in physics is inherently flawed, because statements assigning probabilities to events, or asserting that the events are random, form a deductively closed system from which no factual statements about what happens physically about those events follows." Papineau, 2002. For instance, one cannot identify probabilities with the actual frequencies in repeated experiments because they do not equal them in any finite number of repeats, and infinitely repeated experiments do not occur. And in any case, no statement about frequencies in an infinite set implies anything about a finite subset unless it is a typical subset. But typical is just another probabilistic concept, not a factual one. So that would be circular. Hence, notwithstanding that they are called probabilities, the pi in a stochastic theory would be purely decorative, and hence the theory would remain a mere something possible happens theory, were it not for a special methodological rule that is usually assumed implicitly. End quote. Okay, and so there David's talking about the physical reality or otherwise of probabilities, and he's done a wonderful lecture about this that can be found on his own website and I think the Constructor Theory website about the physics of probability, I think it's called, something like that. And he's quite right here about the philosophical difficulties of applying probabilities in real life. So, for example, if we take a coin and it's a fair coin, a supposedly fair coin, and we're flipping it, and we expect to flip it out of 100 times, we'd expect 50 times heads and 50 times tails. It's very rare that that ever actually comes up. You get close to that, and you get asymptotically closer to the 50-50 over time, but you never get exactly 50-50. And we wouldn't expect, in truth, to get exactly 50-50, but rather something close to 50-50. 47-53 or something like that would still comport with our general understanding of probability. But in what way does probability refer to real life? If you're not getting exactly 50-50 every single time you throw a fair coin 100 times, what does that mean? What does it mean to say that it always comes up 50% heads and 50% tails when it doesn't? It means that it's supposedly one view of probability is if you were to throw it an infinite number of times, then 50% of those would be heads and 50% tails. But that's an unfalsifiable claim. It's not a claim about physical reality. If you want to make a claim about physical reality, then the claim has to be testable. But you can't possibly test an infinite number of throws of the coin. So that seems to be a problem for probability. And David deals with this in his talk, which I recommend to everyone. Okay, and just almost as a postscript here, did Popper ever say falsification was sufficient to establish a theory as scientific? Not at all. The logic of scientific discovery is near to 500 pages, and it defends the criteria of demarcation, among other things. In that book, he also details what crucial experiments are. He said all this back in the 1930s, and there's a free version of the logic of scientific discovery online. You can just look for it, a PDF version. And that was published in 1959, so it's got some updates from Popper himself. David and others have said it again, and I say it now. Popper understood that any purported falsification could mean one of two things logically. It could mean the theory is false, or the experiment was flawed. But this is not a problem for science. We make progress by refuting theories in this way regardless. What we do not do is confirm we are correct. Chapter 4 of The Logic of Scientific Discovery is in fact titled Falsification Ism. If it was as simple as some people seem to think, or Popper was as naive as some people seem to think, one might expect that chapter to run to a few sentences, or maybe a couple of paragraphs. But no, Popper spends pages 57 through to 73 defending his thesis against all manner of objections. And he doesn't stop there.
The whole point is that his epistemology, his philosophy of science, is not summed up by those 16 pages. It is summed up rather well by the other 486. Falsification is but a part of the greater whole. Popper was dealing with problems in science. What did it mean for Eddington's experiment to refute Newton but not Einstein? Was Einstein considered true now and Newton false? Was that it? Was Einstein simply more probably true? Could we measure that probability? One could well spend many episodes of a podcast like this doing little more than discussing Popper's epistemology as explained in The Logic of Scientific Discovery. Perhaps one day I will, for he seems to me to be such an underrated genius that so many claim to have read, and yet it seems to me have misunderstood entirely. It is as if those 16 pages about falsification ism in The Logic of Scientific Discovery were only 16 words, and that the rest of the chapter didn't exist, much less the rest of the book, and much less all of his other books and dozens of academic papers, journal articles and lectures. But he continues to be painted as naive, or not anticipating aspects of science difficult to test in practice. Those who try to explain his ideas more fully than the caricature that often passes for popularising of Popper are often ridiculed as the Popperazzi I've heard recently. That kind of reaction against Popper isn't entirely unique in philosophy, but it is almost rather unique to philosophy, although not completely, because physics suffers from this as well. Many physicists, when you talk to them, can tell funny stories of emails received from someone or other who claims to have, for example, proven Einstein wrong, perhaps with an algebraic proof. Such people who claim to have proven Einstein wrong rarely go to the trouble of trying to engage with the experiments. They look at the mathematics and refuse to believe that their common sense notion could possibly be false. Galilean relativity, they think, must somehow be at base true, so they try their hand at a mathematical disproof. But they've engaged only with the Lorentz transformations, for example, the very basics of special relativity. They prove somehow that the speed of light is not constant. Physicists know the feeling of dealing with these people, and they chuckle with each other about such stories. Or from the next inventor who sent them an idea for a perpetual motion machine or whatnot. These people haven't actually read much of relativity or about the conservation of energy. They've read perhaps a popular account or picked up a high school text and learned enough to attribute to Einstein only part of the story. To those physicists, I say, that cranky engineer has a counterpart in philosophy. They are the people who've read the popular account. It happens with many prolific writers who solve deep problems. Because the problem is deep and the solution often subtle, it can be tempting to shoot off a blog post or an email or a tweet about how Einstein was wrong, that relativity meant the speed of light is constant, or that time slows down the greater one's velocity is. It's a tempting prospect for someone new to the field or a casual reader of the field. It's so tempting, it might even cause someone to write a blog post about how Popper was wrong about falsification. And those that have read beyond the Popperian headlines are terribly naive about how science actually works. So let me leave this episode with some words directly from Popper himself. I'm going to read from Unended Quest, an intellectual autobiography, on page 42. Popper writes there that, quote, "My main idea in 1919 was this. If somebody proposed a scientific theory, he should answer, as Einstein did, the question, under what conditions would I admit that my theory is untenable? In other words, what conceivable facts would I accept as refutations or falsifications of my theory?" And I'm skipping a little, and he says, "I still uphold this. But when a little later I tentatively introduced the idea of falsifiability, or testability, or refutability of a theory as a criterion of demarcation, I very soon found that every theory can be immunized. This excellent term is due to Hans Albert, against criticism. If we allow such immunization, then every theory becomes unfalsifiable. Thus we must exclude at least some immunizations." So I just pause there, end quote. That's 1919. In 1919, he is already considering objections to the falsification criterion. The people today who claim that falsification is too simple an idea in the philosophy of science, and moreover attribute that position to Popper, haven't read Popper. Given that he considers these so-called immunizations, given that he considers ways in which the falsification criterion can itself be problematic and not as straightforward as a naive falsificationist might think. So I'll continue to read Popper. "On the other hand, I also realise that we must not exclude all immunizations, not even all which introduced ad hoc auxiliary hypotheses. For example, the observed motion of Uranus might have been regarded as a falsification of Newton's theory. Instead, the auxiliary hypothesis of an outer planet was introduced ad hoc, thus immunising the theory. This turned out to be fortunate, for the auxiliary hypothesis is a testable one, even if difficult to test, and it stood up to tests successfully. All this shows not only that some degree of dogmatism is fruitful, even in science, but also that, logically speaking, falsifiability or testability cannot be regarded as a very sharp criterion. Later, in my Logique de Forschung, the logic of scientific discovery, I dealt with this problem very fully. I introduced degrees of testability, and these turned out to be closely related to degrees of content, and surprisingly fertile. Increase of content became the criterion for whether we should or should not tentatively adopt an auxiliary hypothesis. In spite of the fact that all this was clearly stated in the Logic of Scientific Discovery of 1934, a number of legends were propagated about my views. They still are. First, that I had introduced falsifiability as a meaning criterion rather than as a criterion of demarcation. Secondly, that I had not seen that immunisation was always possible and had therefore overlooked that since all theories could be rescued from falsification, none could simply be described as falsifiable. In other words, my own results were, in these legends, turned into reasons for rejecting my approach. End quote. And I'll just make this personal reflection here on this idea that, it's a very simple concept that Popper pointed out that the criterion of demarcation is not a criterion of meaning. So although he was saying that this separates science from non-science, that the ability to do an experiment demarcates the scientific enterprise from other kinds of knowledge, it's not saying that nothing else has any meaning or isn't useful. Quite the contrary. After all, Popper was very interested in political philosophy, political science, or political philosophy, we should say, and morality. He didn't think those things were meaningless. He didn't think that philosophy was meaningless. That's what he was spending most of his time on. Those things are important. So when people talk about, let's say, multiverse theories that are not the quantum multiverse theory, these cosmological multiverse theories, well, I would call it the megaverse, okay? The idea that there are other universes out there that have different physical laws. This is a very different kind of multiverse to the multiverse that quantum theory forces us to understand the world through. These other megaverse theories, where there might be universes out there with different physical laws, there are some physicists who are very upset about the fact that these might be ruled out of science. Now, I would rule them out of science. I would say, well, they're not testable. There's no testable prediction. But there are scientists, there are physicists who say, well, this is a problem for the demarcation criterion. This is a problem for falsification. Because we should be able to call these theories scientific. Why? I don't understand the problem. Like, what they're upset by is that we're going to regard such a theory of other universes with different physical laws, as metaphysical. And that somehow that is, in a way, lessening that theory. No, it's not. You can still go on and do your mathematics and do your physics of these alternate theories, of these other kinds of multiverse. In fact, you can test them in a certain way. Some people might be interested in the work of cosmologist Luke Barnes. He's from Australia, and one of his projects is actually to look at the question of fine-tuning. And I think he's not the only one. There are other physicists who do this kind of thing, other cosmologists who do this kind of thing. And they use computers. They use supercomputers and simulations of universes with different laws of physics, and see what happens in those things. So to a certain extent, they're kind of testable. Let's see what happens in such a universe where you've got different physical laws. And they do this for the purposes of fine-tuning. Are any of those universes that they simulate able to support complex chemistry, life, and so on? Whatever the case, it's no insult to call a particular theory or idea metaphysical. It's no insult. It's scientism, rank scientism, to insist that if your theory cannot be tested by experiment, that it nonetheless should be regarded as science, then you've got a bias. You think that scientific knowledge is in some way superior to, better than, certain other kinds of knowledge which might be very legitimate. Here's a metaphysical theory. Reality exists. The universe really exists. It's not just all being dreamed by you. That's a metaphysical theory. That's not a scientific theory. There's no experiment that I can do to test whether or not I'm dreaming right now or not. Maybe when I go to sleep at night and I have a dream, I'm dreaming within a dream. I'm already here in a dream. Or maybe I exist inside of a simulation. These are metaphysical theories. My claim that all of that is nonsense, that we are not dreaming, we're not in a simulation, there's not an evil demon deceiving us. My theory that all of that is quite correct, that none of this is true, that in fact reality just is, and we exist inside reality, that metaphysical theory is just as important as any scientific theory, and I'm willing to defend that metaphysical theory. And it's no insult to call it metaphysical. It's no insult to call a certain theory a moral theory or a mathematical theory. Metaphysics isn't an insult. Now, pseudoscience is an insult, but I wouldn't regard ideas about other universes with different physical laws as being pseudoscience. It's a legitimate area to investigate. It could be fun, philosophically interesting. You don't have to call it science, and importantly, you don't have to go throwing away the criterion of falsifiability because there's one very esoteric area of theoretical metaphysical cosmology that you happen to enjoy doing and exploring and thinking about. It's only ever, and I'll just end on this, it's only ever the theoretical physicists that have a problem with the falsification criterion. The ornithologists aren't worried. The geologists aren't concerned. The pharmacologists don't get into these debates. It's only the theoretical physicists that get upset at Popper. And that should be very, very telling. It's because they operate right at the very margins of what science can do, and that's great. That's great. They need to keep pushing those boundaries. But they have to recognize when things are testable and when things aren't testable, because if they're not testable, then their ideas can't be handed over to the managers at the Large Hadron Collider or to the people in charge of the Hubble telescope. There's no observation that can ever show that any of their ideas are wrong. And if they can't, well, you're doing metaphysics. Could be interesting, could be entertaining, could even inform research projects in real science, but it's not science, and it's no big deal. Anyway, there we have it in Popper's own words, that he wasn't a naive falsificationist. He did understand it all, he understood the objections, he spoke with scientists, including physicists. He spent his life defending that thesis, and if you take it seriously and really investigate it and think of all the ways critical rationalism, might be false, and then read what he said in his own words, you just might be convinced he was right, rather than convinced he was mistaken by a headline in a brief article that mangles what he meant in order to refute a straw man. If you're getting value out of these podcasts, or my YouTube videos or website, why not consider donating? I've now got a Patreon account at Brett R. Hall, all one word. So that's Brett R for Robert, Hall, all one word. Or if you go to my website, www.bretthall.org, there's a donate button now on my front page if you'd like to make a small one-off donation. Thanks for any support as I'm trying to devote more time to this endeavour. Bye-bye.